In the previous lecture, we discussed effect of pressure on solubility, Henry's law, vapor pressure of liquids, factors affecting vapor pressure, Raoult's law and ideal solutions. In today's lecture, we are going to discuss non-ideal solutions, types of deviations from ideality, azeotropic solutions, colligative properties, relative lowering in vapor pressure and Raoult's law. Study of colligative properties is very important because by measuring any of the colligative property, we can calculate the molecular mass of the solute from which solution has been made. Now, we are going to discuss non-ideal solutions first. In general, most of the solutions deviate from ideal behavior. There are two types of deviations, positive deviation and negative deviation. Such solutions are called non-ideal solutions which deviate from ideal behavior. First type of non-ideal solutions are those which show positive deviation. These solutions possess some of the characteristics. They do not obey Raoult's law. Delta H mixing is always greater than 0, means there is endothermic dissolution and heat is absorbed during solution making. Delta V mixing is also greater than 0, volume is increased after dissolution. Pa is greater than P naught A x A and Pb is greater than P naught B x P. Here Pa is partial vapor pressure of solute and Pb is partial vapor pressure of solvent. Therefore, Pa plus Pb is always greater than P naught A x A plus P naught B x B. Here is the Raoult's law graph. You can see this in the graph that Pa is greater than P naught A x A and Pb is greater than P naught B x P. Similarly, Pa plus Pb is greater than P naught A x A plus P naught B x B. Solvent solute attractive forces should be weaker than solute solute and solvent solvent attractive forces. Solute and solvent have different shape, size and character. Solvent and solute escape easily, showing higher vapor pressure than the expected value. An example of such liquid mixture is ethanol and normal hexane. The hydrogen bonding in ethanol molecule are broken by the normal hexane molecules coming in between the ethanol molecules. As a result, the escaping tendency increases, thereby increasing the vapor pressure of individual components and therefore, a positive deviation is observed. Some examples of the solutions which show positive deviations are acetone and ethanol, acetone and carbon disulfide, water and methanol, water and ethanol, carbon tetrachloride and toluene, carbon tetrachloride and chloroform, acetone and benzene, carbon tetrachloride and methanol, cyclohexane and ethanol. Next, we are going to discuss the solutions which show negative deviations. These solutions also possess some characteristic properties. These properties are: they do not obey Raoult's law, delta H mixing is always less than 0. It means exothermic dissolution takes place and heat is evolved during the solution making. Delta V mixing is also less than 0, which means volume is decreased during dissolution. Pa is less than P naught A x A and Pb is less than P naught B x B. Similarly, Pa plus Pb is less than P naught A x A plus P naught B x B. You can see all these things in the graph. Here Pa is less than P naught A x A, Pb is less than P naught B x B and Pa plus Pb is less than P naught A x A, P naught B x B. Solute-solvent attractive forces should be greater than solute-solute and solvent-solvent attractive forces, and solute and solvent have different shape, size and character. Escaping tendency of both components, solute and solvent, is lowered, showing lower vapor pressure than expected ideally. An example of solution exhibiting negative deviation is chloroform and acetone, the molecular interaction of which you can see in this figure. There is a hydrogen bonding between the acetone and chloroform molecule. As a new force of attraction exists between the molecules, the partial vapor pressure decreases. Some examples of this type of non-ideal solutions are acetone and aniline, acetone and chloroform, methanol and acetic acid, water and nitric acid, chloroform and diethyl ether, water and HCl, acetic acid and pyridine, chloroform and benzene. Now you know that many solutions behave as non-ideal solutions. Very large deviation from ideality leads to the formation of special kind of mixtures known as azeotropes, azeotropic mixtures or constant boiling mixtures. Azeotropic mixtures is a special class of liquid mixtures that boils at a constant temperature. At this condition, it behaves as if it was one component with one constant boiling point. A boiling liquid mixture at the azeotropic composition produces a vapor of exactly the same composition and the liquid does not change its composition as it evaporates. There are two types of azeotropic mixtures: minimum boiling azeotropic mixtures and maximum boiling azeotropic mixtures. Now we will discuss minimum boiling azeotropic mixtures. When the positive deviations from ideality are sufficiently large, the mixture is said to form a minimum boiling azeotrope or minimum boiling azeotropic mixture. Here you can see the phase diagram for such type of azeotropic mixture. This figure shows the constant pressure phase diagram for a minimum boiling azeotropic mixture of carbon disulfide and acetone. The characteristic of such mixture is that the total pressure goes through a maximum and therefore the temperature goes through a minimum. At this point, the concentration in the vapor phase is the same as the concentration in the liquid phase. This concentration is known as azeotropic composition. In this case, it is 0.61 mole fraction of carbon disulfide. At this point, the mixture boils at a constant temperature. In this case, it is 39.25 degrees Celsius at 1 atmospheric pressure. At this point, the mixture boils without change in composition. There are several liquid pairs which form minimum boiling azeotropic solutions. Some of these are water and ethanol, which boils at 78.13 degrees Celsius. In this, 95.97% ethanol is taken. Second pair is pyridine and water, In this, 57% of pyridine is taken and this solution boils at 92.6 degrees Celsius. Ethanol and benzene also shows this type of azeotropic solution. In this solution, 32.4% ethanol is taken and it boils at 67.8 degrees Celsius. Acetic acid and toluene also form minimum boiling azeotropic solution and it boils at 105.4 degrees Celsius with a composition of 28% acetic acid. Another type of azeotropic solutions are maximum boiling azeotropic solutions. These type of azeotropic solutions are formed when negative deviations are sufficiently large and the total pressure curve in this case passes through a minimum, giving rise to a maximum in the temperature, that is boiling point. This figure shows the constant pressure phase diagram for a maximum boiling azeotropic mixture of acetone and chloroform. The azeotropic composition is 0.345 mole fraction acetone. At this point, the mixture boils at constant temperature 84.5 degrees Celsius at 1 atmosphere pressure and without change in composition. There are several liquid pairs which show maximum boiling azeotropic behavior. These are nitric acid and water. It boils at 125.5 degrees Celsius and it contains 68% of nitric acid. Acetic acid and pyridine, which contains 65% of pyridine, boils at 139 degrees Celsius. Chloroform and acetone containing 80% of chloroform boils at 65 degrees Celsius. Hydrogen chloride and water, which contains 79.8% water, boils at 108.6 degrees Celsius. Azeotropic mixtures cannot be distilled with simple distillation techniques. Some special distillation techniques are to be employed. For example, in the case of ethanol water, one cannot recover more than 89.4 mole percent ethanol using ordinary distillation because as the mixture becomes azeotropic at this point. Some special type of separation techniques like azeotropic distillation must be used to separate azeotropic mixtures. Often the equipment and setup used is unique for each mixture. The dilute solutions show more or less ideal behavior as the heat and volume changes accompanying the mixing of solute and solvent are negligible for all practical purposes. Dilute solutions obey Raoult's law. The dilute solutions more or less show ideal behavior because in case of dilute solutions, the heat change and volume change during the dissolution process is negligible. Normally, all the dilute solutions obey Raoult's law. Dilute solutions containing non-volatile solute exhibit some special kind of properties known as colligative properties. Certain properties of solutions depend only on the number of particles of solute. These particles can be molecular or ionic. These properties, which depend only on the number of particles of the solute, are known as colligative properties. Colligative properties does not depend upon the nature of solute. For example, if you have taken 1 molar glucose solution and 2 molar glucose solution, all the chemical properties of these two solutions will be similar, but colligative properties of these two solutions will be different as number of particles of glucose in both the solutions are different. There are 4 types of colligative properties: relative lowering in vapor pressure, elevation in boiling point, depression in freezing point and osmotic pressure. Colligative properties are the properties of dilute solutions. Hence, these properties are often termed as colligative properties of dilute solutions. These properties are related to one another. Hence, if one of the properties is measured, the other can be calculated. The importance of these properties lies in the fact that they provide methods for the determination of molecular masses of dissolved solutes. The results are excellent if three conditions are satisfied. First condition is the solute must be normal, means the solute must not dissociate or associate in the solution. The second condition is the solution must be very dilute, and the third condition is the solute must be non-volatile. The colligative properties really depend on the escaping tendency of solvent molecules from the liquid phase. Vapor pressure is a direct measure of escaping tendency, so we can use these terms more or less interchangeably. Here you can see in this phase diagram that vapor pressure of solution is less than the vapor pressure of pure solvent at a particular temperature. When a non-volatile solute is added to a solvent, the vapor pressure is lowered. This is because the solute molecules occupy the surface, and so the percent surface area occupied by the solvent decreases, and the solute particles at the liquid vapor boundary block the solvent particles from jumping into the vapor state. This you can see in this figure. In first figure, there are solvent particles only, but in second figure, some solute particles has occupied the surface, and hence the number of solvent particles which can escape out in vapor phase becomes less. Hence, the vapor pressure in second case is lowered. Because of this phenomena, the rate of evaporation and vapor pressure both decreases. Now, we are going to discuss relative lowering in vapor pressure. If P naught B is the vapor pressure of pure solvent and Ps is the vapor pressure of solution, then P naught B minus Ps is lowering in vapor pressure, and if we divide lowering in vapor pressure by the original vapor pressure of pure solvent, that is P naught B, we will get relative lowering in vapor pressure. Hence, P naught B minus Ps upon P naught B will be equal to relative lowering in vapor pressure. Raoult in 1886 established a relationship between relative lowering in vapor pressure and composition of the solutions after a series of experiments in various solvents. The relationship is known as Raoult's law. Now, we are going to derive Raoult's law for dilute solutions. Raoult's law states that the relative lowering in vapor pressure of a dilute solution is equal to mole fraction of the solute present in the solution. Now, we are going to derive a relationship for Raoult's law for dilute solutions. When a non-volatile solute is dissolved in a volatile solvent, a fraction of the surface of solvent is blocked by solute molecules where no evaporation occurs. Thus, under similar conditions, the vapor pressure is decreased. The vapor pressure of the solution thus depends upon the number of molecules of the solvent present on the surface of the solution. The number of such molecules is proportional to the mole fraction of the solvent. Now, you know that Ps is equal to Pa plus Pb. Here Ps is the total vapor pressure of the solution, Pa is the partial vapor pressure of solute, and Pb is partial vapor pressure of solvent. as solute is non-volatile, hence Pa will be equal to 0. Putting Pa equal to 0, you will get Ps is equal to Xb P naught B. As Xa plus Xb is equal to 1 means mole fraction of solute plus mole fraction of solvent is equal to 1. Hence, you can take Xb is equal to 1 minus Xa and can put this value at the place of Xb. Now, you will get Ps is equal to 1 minus Xa multiplied by P naught B. On rearranging, you will get Ps upon P naught B equal to 1 minus Xa, or you can get P naught B minus Ps upon P naught B is equal to Xa, means relative lowering in vapor pressure is equal to mole fraction of solute. This is Raoult's law for dilute solutions. If a solution is made by dissolving Wa grams of the solute in Wb grams of the solvent with Ma is the molecular mass of the solute and Mb is the molecular mass of the solvent, then number of moles of solute will be equal to Wa upon Ma and number of moles of the solvent will be equal to Wb upon Mb. Then relative lowering of vapor pressure will be equal to mole fraction of solute and we will get the expression P naught B minus Ps upon P naught B equal to Wa upon Ma upon Wa upon Ma plus Wb upon Mb. If the solution is very dilute, Wa upon Ma can be neglected in denominator as compared to Wb upon Mb. Then the second equation comes out to be P naught B minus Ps upon P naught B equal to Wamb upon Mawb. This relationship is useful in the determination of molecular mass of dissolved solute by measuring relative lowering of vapor pressure. We can modify the Raoult's law for better results. We can take the reciprocals of both the sides from Raoult's law expression and we will get P naught B upon P naught B minus Ps is equal to Na plus Nb upon Na, which is again equal to 1 plus Nb upon Na. On rearranging, we will get P naught B minus Ps upon Ps, which is equal to Nb upon Na, which is again equal to Wamb upon Mawb. This equation gives accurate results and is easier to apply. We can practice Raoult's law equation with the help of some examples. Estimate the vapor pressure of a 40% weight by weight solution of ordinary cane sugar in water. The vapor pressure of pure water at this particular temperature is 26 torr. You know that molecular formula of cane sugar is C22O11H22 with molecular mass 342 grams per mole. 100 gram of solution contains 40 grams of sugar and 60 grams of water. Hence, it contains 40 upon 342 equal to 0.12 moles of sugar and 60 upon 18 equal to 3.3 moles of water. Now, the mole fraction of water will be equal to number of moles of water upon total number of moles, which is equal to 3.3 upon 3.3 plus 0.12, which is again equal to 0.96. Hence, the vapor pressure will be mole fraction of water into the vapor pressure of pure water at this temperature, which is equal to 0.96 into 26 torr, which is again comes out to be 25.1 torr. In today's lecture, we discussed non-ideal solutions, types of deviations from ideality. There are two types of deviations, positive deviation and negative deviations. azeotropic solutions. There are two types of azeotropic solutions: azeotropic solutions with minimum boiling and azeotropic solutions with maximum boiling point. Colligative properties. We defined colligative properties and we have discussed one colligative property, that is relative lowering in vapor pressure, and derived a relationship for Raoult's law for dilute solutions. In our next lecture, we will take some other examples for better understanding of Raoult's law and experimental measurements of relative lowering of vapor pressure.